This week we're working with section 6.3 in Envision, and this is exponential growth and decay. So for exponential growth, we have the formula f of x equals a times 1 plus r raised to the x. And this is very similar to what we did the previous week, which is a times b to the x, except b is now 1 plus r. And that's because we're talking about growth in the context of problems. So let's look at the first problem here. The world population in 2000 was approximately 6.08 billion. The annual rate of increase was about 1.26%. Find the growth factor for the world population. So the first thing I'd like to do with these is take the rate of increase is 1.26%. Now in my function, I'm not going to have percents, so I have to convert this to a decimal. So 1.26% converts to, move the decimal twice, and you get 0.0126. So 0.0126 is R. The growth factor for the world population is a little different though. That's going to be everything in 1 plus R. So highlight that so you can see it. So this whole thing, 1 plus R, is the growth factor. So the growth factor for this would be 1 plus 0.0126 or 1.0126. So that's the growth factor. And it says, suppose the rate of increase continues to be 1.26%. Write a function to model the world population. Well, we have the growth factor. We have A, so we can write that equation. So in 2000, it was approximately 6.08 billion. So that's what we start with. So our function is going to be f of x equals 6.08. And so this is going to be in billions. I'm not going to write out all the zeros. This is times 1.0126 raised to the x, and that would be our function. So in the C part, it's asking us to use this. So I'm not going to calculate this directly here. You can on a calculator, but I'll show you how to do it. So it says, let x be the number of years past the year 2000. Find the world population in 10 years, or in 2010. So since x is the number of years past 2000, we're just going to take this 10 and say, what is f of 10? So 6.08 times 1.0126 raised to the 10th. And that would be, it comes out to 6.89 billion. Okay, so let's do another example here. Let's do this second one. So a computer valued at $6,500 depreciates at the rate of 14.3% per year. Write a function that models the value of the computer. Okay, so this one is decreasing. So exponential decay is what this is. So exponential decay is going to be, so the general formula would be f of x equals a times 1 minus r to the x. So it says write a function that models the value of the computer. So what we're going to do is first find the growth factor, or this is a decay factor. So it's depreciating at the rate of 14.3% per year. So let's make that a decimal number. So that's going to be 0.143. And then we have to subtract that from 1. So we'll go 1 minus 0.143. And so 1 minus 0.143 equals 0.857. So I'm going to round that up to 0.86. And find a function that models the value of the computer. Well, we have the growth factor, so we have f of x equals the initial value of 6,500 times 0.86 raised to the x. So it says find the value of the computer after 3 years. So we just plug in 3 to that. And using a calculator, which again I am using Desmos, and I just take 0.86 raised to the third power, and then I multiply by 6,500. Okay, so we're going to have sorry about the weight here. Okay, so that comes out to approximately 4095. This would be dollars. So after 3 years, a computer that is losing 14.3% per year in value, and you paid $6,500 for it, would be worth $4,095. Okay, so let's do another one. So this one is the population of a certain animal species. And this decreases at a rate of 3.5% per year. You have counted 80 of the animals in the habitat you are studying. Write a function that models the change in the animal population. So a couple things here. It is decreasing at a rate of 3.5% per year. So the first thing I like to do is change that percent to a decimal. So it's going to be 0.035. And then to find the growth factor, we're going to take 1 minus 0.035, and that will give us our growth factor, which is 0.965. And then for the function, we just have the initial number of animals, which is 80, times 0.965 raised to the x. Okay, so this next part says graph the function, estimate the number of years until the population, should say first, drops below 15 animals. So I'm going to move to Desmos and take a look at that. All right, so I've graphed the function 80 times 0.965 raised to the x, and here it is. And we're just looking for when the y value is first below 15. So the question was estimate the number of years until the population first drops below 15 animals. And so it starts at 80, and if we just trace this number down, we can see when is the y value 15 or less. And it looks like it's somewhere, it's 15 there, and then so somewhere in there. So somewhere around 47. So this would be at 47 years. So 47 years later. Okay, so we're going to go to a different question here. So let's do this one. A new car that sells for $18,000 depreciates 25% each year. Write a function that models the value of the car. Find the value of the car after 4 years. So I'm going to just jump straight to the function with this one because it's relatively easy to do this. So I'm going to highlight 18,000. That is my A value. And so I start with 18,000 and then multiply times 1 minus 0.25 raised to the x. And so I would get f of x equals 18,000 times 0.75 raised to the x. And it says find the value of the car after 4 years. We're looking for f of 4. So 18,000 times 0.75 raised to the 4. And then we can find that value. So 0.75. First I raise that to the 4th power. And then I multiply. by 18,000. That gives me $5,695.31. So the car has depreciated to $56.95 after 4 years. Okay, and we'll just do one more of these. I'm going to do this bear population problem. So it says the bear population increases at a rate of 2% per year. So increases at a rate of 2% per year. And jump to changing 2% to a decimal, which is 0.02. And it says there are 1,573 bears this year. So that would be my A value. Write a function that models the bear population. How many bears will there be in 10 years? So just like the other ones, these get a little bit repetitive when you start working with them. It would be f of x equals my initial value times 1 plus my rate raised to the x. So f of x equals 1573 times 1.02 raised to the x. How many bears will there be in 10 years? Is f of 10. Okay, so then we have 1.02 raised to the 10th power. And then that's times 1573. So this is approximately, because we can't have partial bears, this is approximately 1917. So 1,917 bears after 10 years.